Hey everybody, welcome back to another round of physics, and yeah, let's get going. Last time we talked a little bit about vector fields and how to go about measuring vector fields and what they're trying to particularly convey. In the context of this class, we're interested in looking at the force field, for lack of a better term, in the vicinity of a charge. And we talked about taking little test charges to measure the strength of those interactions at different locations surrounding the charge. And that's what we have visualized for you here. Now, generally speaking, we're not interested in the forces at every location in space. And the reason for that has something to do with this next video that we have. So again, I've got the sheet, and you notice I'm dropping a ball. And that's a racquetball, just in case you want to know. But now I've got a tennis ball, and the interesting thing is, notice that the tennis ball essentially does the exact same thing. And I can keep swapping. It doesn't matter if it's a tennis ball, or if it's a racquetball, or maybe a styrofoam ball, or a baseball, or a pool cue. You'll notice that they are all essentially doing the same thing. And so the question becomes, is there something going on that's independent of the ball that I'm using? Okay? And of course the answer is yes. The thing that's independent is the underlying surface, right? The reason that all of those spheres behave the similar way is because the underlying surface which they interact with stays the same. Okay? Now that's the idea that we're going to pursue, the idea that there's some sort of quantity that just depends on this central charge and does not depend on the test particle itself. Okay? And indeed, as the title of the slide would suggest, that is what we refer to as the electric field. So how do we get the electric field? The first thing that I'm going to start off with is an expression, of course you're already familiar, the Coulomb force. Okay? Now let me be a little bit more specific here. We know that forces deal with interactions between systems and surroundings. And so to be very specific here, I'm thinking about that large Q as being the surroundings, and this test charge, my measurement device, as being the system. And so this expression will tell me how my surrounding interacts with my system. Okay. Well, now I'm just going to do a little bit of, for lack of a better word, I'll say math. And it's nothing fancy. I am just simply going to separate out the expression, the quantity, the physical quantity that involves my system from everything else. And you notice that it doesn't matter here. If I move this to the other side, as we'll do here, okay, the quantity that is left over on the right side of this equation has nothing to do with my system whatsoever. K, constant. Q is a charge for the surroundings, the thing that's doing the interaction. Okay. R is my position in space with respect to that central charge. Okay. And so indeed, thinking about that video clip, this expression here describes the influence of the surroundings, the influence of large Q. In the video, the analogy is that this represents the surface on which I am dropping those spheres. Now that helps us out, that physical quantity which describes the landscape, that is the physical quantity that we refer to as the electric field. And so a different way to think about it is the electric field is the force of the interaction divided by the charge of the system. And that quantity ends up being independent of, the system itself. Now, we use the expression for the electric field, we use E, capital E. And here I have to be careful. The question was asked of me at one point in time, do I grade for vector signs? Okay. And the answer is yes. And here's one warning that I have for you, because we have used E at other points, namely in our mechanics classes. Generally, E without the vector symbol, if you write that down, or if you're just doing some problem and you write that down at some point, I guarantee you that most people are going to think about energy. Perhaps total energy, I'll put that in parentheses. But my guess is 9 times out of 10, somebody's going to think of this as being the energy or the total energy. Okay? And you can see that that varies dramatically from this new physical quantity that we've introduced called the electric field. Okay? So yes, you need to be careful with your vector signs. Okay? And notice the same thing. If you say, well, what happens if I want to write the magnitude of E? I would recommend, just so that you're being clear with your communication, that you include the vector sign and then put magnitude symbols around it. Okay? That will be very clear to anybody, engineers, physicists, chemists. It doesn't matter who sees that. They will understand exactly what you mean if you write it this way. Okay? So that's my warning to you. Okay? Now, to give you a sense, another thing about this equation. So if I go back and think about, the force field for a second, okay, the field around the charge, you could say, well, if I go back and I want to think about what does the electric field look like in the vicinity of a charge, this equation now gives me a sense of how long I should draw my vectors. And we had some discussion about this in the past, but essentially if I'm at one location and then I go, say I'm at a distance of 1 away from that central charge, if I double the distance, now my arrow should be 1/4 the size. So really what I want to say is this equation tells us how quickly that hill dies off. Be a different way of kind of thinking about it. Now, another point in the physics stuff, if you will, is how we represent the electric field in a vector map. Now, in the previous discussion, I said, well, if you want to scale it appropriately, the appropriate way to do it is to do the scaling. But you can imagine for a second that if I get far enough out, it might seem like there's not a vector there at all. And in some sense, there isn't, right? If I get far enough away, the vector is going to be so short in magnitude that I won't even be able to see the length of the arrow anymore. Okay? So generally, you will see a vector field indicated in one of two ways. One of them is where the scaling is actually taken into account. So I get further and further away, and eventually these become little dots. And now, I can't really get very much information here because it's hard for me to see the arrow at all. Okay? Alternatively, there is a second representation, which is just simply trying to give you a sense of the directions. Okay? So it is common to see a vector map drawn like this, which is only trying to emphasize the direction of the vectors, not the magnitudes. And of course, it's understood, since you have this equation now, it is understood that the magnitude of the vector goes like 1/r². Okay. Well, a couple of conceptual questions. It doesn't hurt to have a couple of those. So the first question, given the direction of the electric field, what direction is the Coulomb force? You got it? Yeah, pause the video if you don't. That's perfectly fine. Okay. And here we remember, what does scalar multiplication do to a vector? Yeah, you got it? Yeah, good. And we have here to remember that what does scalar multiplication do to a vector? So the definition of the electric field is the Coulomb force divided by the test charge, or if you want to, put in here the system, the charge of the system. Well, we could rearrange that. We could say the electric field, the thing that contains all of the stuff involved with the surroundings, and I multiply by the charge of the system. That tells me what the interaction is between the system charge and the surroundings. Okay? But scalar multiplication doesn't change directions of vectors. This means that, well, I should be very careful here, because what could happen? I say what could happen, but yeah, there's two options here. Okay? We could say, well, either the system charge is positive, and then the Coulomb force is in the same direction as the electric field. Okay? Or the system charge is negative, and that means that the Coulomb force is in the opposite direction of the electric field. Right? So don't forget, right? Negative signs flip directions of vectors. Okay? So if you can map out the vector field representing the Coulomb force, you immediately have the vector field that represents the electric field. Okay. Here's another question for you. Does the electric field obey superposition? Yeah. The answer. Now, I've asked about the electric field, but what's the electric field related to? Yeah, remember, it's related to the Coulomb force, right? Now I'm going to use that. It's the Coulomb force per unit charge of my system. Okay, that is the definition of the electric field. So the question then becomes, do forces obey the superposition principle? And the answer is yes, right? When we want to calculate out a net force, what we do is we look at the individual forces and add them together. And that is the idea of superposition. So the upshot is that because forces obey superposition, the electric field also obeys the principle of superposition. In other words, if I want to find what the electric field looks like due to multiple charges that I'm considering to be the surroundings, I simply have to find the electric field due to each charge and then add them all together. Right? So I'll just write this down for completeness. Cool, huh? Let's say that I have 3 charges that I'm considering to be my system. Okay, so I have charge 1, I have charge 2, and I have charge 3. And I'll just put them at random locations. Okay? And now generally what happens is that you will be asked in the homeworks, for example, to calculate the electric field at a particular location in space. Okay? So we'll say, I'll mark it with an X. We'll say, okay, you'll be asked to find the electric field, the net electric field at that location in space. Okay? Generally, and this is a terminology bit, generally the location in space where you would like to find the magnitude or the value of the electric field, that location is often referred to as a field point. So yes, that terminology comes up a lot. We want to know the electric field at a location in space. And there might be something located there or not, right? So we refer to it as a field point. And again, we follow our usual things. If we put an origin somewhere on the plane of the page, you can get the position vector of the field point, something like I usually subscript it field point. You can get the position vector of the charge. We'll go to the -3, or the third charge here. And then you can get the relative position vector pointing from, for example, from the charge to the field point. Lastly for you, and I use this to try to help organize some information. Okay. So the last thing I'll do for you here, and we'll do some more kind of exercises and that kind of thing, okay? But the last thing is I tend to use this chart just to kind of help organize some of the thoughts, because what's going to happen is that we're actually going to end up with 4 different physical quantities that have equations that look roughly the same. Okay? So the first one, of course, and I have it written up for you here, is the Coulomb force. And this is representing, I'll say right over here, we'll call this the interactions column. Okay. Everything on this side, the left side of the page, are going to be physical quantities representing the interaction between the system, which I'm going to use little q to represent, and the surroundings, which I'm using big Q. And so I have both the system and the surroundings in this expression. But we also have now physical quantities that just represent the surroundings, that just involve characteristics of the surroundings. So I'll put that over here in the right column. These are just surroundings, or if you prefer, like I said, I tend to think of like the landscape. And we have now one called the electric field going over there. Notice the units of the electric field are newtons per coulomb, so a force per unit charge. And if I have the total Coulomb force, I can simply find the magnitude of the electric field by dividing out the charge of my system. So that's why I put, if I take this expression, I multiply by 1 over q, I arrive at the value of the electric field for the particular point, the field point that I'm considering. Okay. Alternatively, and this is sometimes where the power comes in, is that if I know the net electric field and I want to determine the force at a particular location in space, I simply multiply by the charge of the system, the charge that I want to actually place at the field point location. Okay, so the last little piece I'll say is, yes, it is a new physical quantity, but the issue is that you already, I shouldn't say the issue. So the brief encouragement that I'll give you here, because what's going to happen is the homework assignment for dealing with electric fields, it's going to feel a lot like the Newton's law problems or the force problems that you've already done, because those two physical quantities are very closely related to one another. And in fact, they're both vectors. They both obey this principle of superposition. And so all of the vector algebra that we've done in the past still applies. Okay. Now, the advantage using the electric field, there we'll see that there's actually two very curious and very interesting ideas that come out of the electric field. Okay. One of them is that charges, we'll discuss this in another video, but I'll give you a kind of a teaser. Okay. One of the interesting ideas is that charges generate a finite amount of electric field. Okay. So if I have a particular charge and I double it, I can say, hey, it produces double the electric field. We'll have to explain what I mean by double and all that kind of jazz. But the issue is that you can use charges to determine how much electric field there is. Okay? Or you can count up how much electric field there is to figure out how much charge is present. Okay? So it's a one-to-one relationship, which is kind of cool. The second thing that comes into play is just like how in mechanics we started off with forces and then we said, hey, this is for the birds. Let's find a scalar quantity that gives us the same information but makes our lives easier from the mathematical standpoint. Okay. We similarly have a scalar quantity that is related to the electric field, and that scalar quantity will help make our mathematical processes easier. Okay? But I know you're excited. That's for another video. So, hey, I thank you for your attention. Keep up the good work. I'll see you next time.